For part 2 of this video, we are going to be covering the half-angle identities. So the half-angle identities can be used to find the exact trig values of non-standard trig angles by multiplying them by 2 and using that value in the half-angle formulas. So here we have the 3 half-angle formulas. You want to copy them down, make sure you have them. The one thing I want to point out is that the plus or minus in front of it, you don't keep it as plus or minus, you choose one or the other. So if your original angle is, let's just say, a second quadrant angle, and you're doing the sine, well, sine's always positive in the second quadrant, you would choose the plus. If your original angle is in the second quadrant and you're doing cosine, cosine's always negative in the second quadrant, you would choose the minus. So you choose one or the other depending on which quadrant the original angle lies. Here are the steps we're going to follow for using the half-angle formulas. First, we're going to determine the quadrant of the angle and then figure out which sign to use, positive or negative, based off which quadrant it lies in. Then we're going to double the angle and just make sure that it falls on the unit circle, because if not, we're not going to be able to use these half-angle formulas. Then we're going to plug the angle into the formula and then substitute in the trig ratios, and finally we're going to simplify. So for our first example, we are going to find the exact value of sine of 7 pi over 12 using a half-angle identity. So as a hint, I would say always convert to degrees. So let's start by converting 7 pi over 12 to degrees. We can do that in the calculator by doing 7 times 180 divided by 12, and that's 105 degrees. So really we're looking for the sine of 105 degrees. Now if I go to my unit circle, 105 isn't on here, so it's not a special angle. So the only way to find the sine of 105 degrees is to use the calculator, but that's going to give me a decimal approximation, but we know that we want exact values. That's why we're using these formulas. Now if I double 105, that gives me 210. 210 is on the unit circle, as you can see, so I am able to use these half-angle identities. So step 2 was to double the angle. So if I double the angle, I get 210. So the sine of 105 degrees is going to be the same as the sine of 210 divided by 2. And then let me backtrack to the formula so I can plug in. The sine of x over 2 is going to be plus or minus. My original angle is 105. 105 is in the second quadrant and sine's positive in the second quadrant, so I'm going to use the plus. 1 minus cosine x over 2. So positive 1 minus cosine x, which would be 210 over 2, and then there's a square root around all of that. Okay, so we've got everything substituted in, we've got the sine figured out. Now we are going to plug in the trig ratios. We know the cosine of 210. It is a value on the unit circle. I can find it. 210's right here. The x value is negative root 3 over 2, so the cosine of 210 is negative root 3 over 2. So let's plug that in. 1. So that'd be 1 minus negative root 3 over 2, which I'm going to turn into a positive, all over 2. And then the final step is to simplify, and there's a lot wrong with this right now, so there's a lot that needs to be done. The first thing I'm going to do is make a common denominator in the numerator, and combine that. So the common denominator would be 2. So that'd be 2 over 2 plus root 3 over 2. So that'd be 2 plus root 3 over 2. Okay, that's what I'll do first. 2 plus root 3 over 2 all over 2. Now, when you have a fraction divided by another fraction, right, 2 over 1 would be the other fraction, you know that you can multiply by the reciprocal. So that would be my next step. And that would leave me with the square root of 2 plus root 3 all over 4. Okay, and there's still more work to be done because technically I have root 2 plus root 3 over root 4 because the square root's over the whole fraction, and we know that we can't have fractions in the denominator, but luckily 4 is a perfect square, so that reduces to over 2. So my final answer, the square root of 2 plus root 3, and I know it looks funny with a root under a root, but you can have that, over 2. And then when I put it over 2, the denominator's not under the radical. Or you could also rewrite that like this, and I would accept either answer. They are both correct, so either or. And that would be considered fully simplified, so we don't have any more work left to do. You can check your answer by making sure your calculator's in degree mode. So hit mode. Where is it? And then the original angle is 105, so I want to do sine 105. Hit enter. And then I want to type in my new answer, which is root 2 actually I don't want to close that parenthesis, plus root 3, double parentheses here so that the calculator knows to take the square root of that entire numerator, over 2. And I see that I get my same decimal value, so I know my answer is correct. Here's a practice problem for you to try. It's the same idea. You're going to follow the same exact steps, except this time you're going to use the cosine formula. So pause it, try it, and press play when you're ready. So when you convert this to degrees, it's cosine 75. And 75 isn't a value on the unit circle, but 150 is. So you are going to find the cosine of 150 over 2. And 75 is in the first quadrant, cosine's positive in the first quadrant, so the sign in front of the radical is going to be a positive. And the formula for cosine is 1 plus cosine 50, 150, over 2. The cosine of 150, you can find it on the unit circle, is root 3 over 2, but it's negative. So 1 minus root 3 over 2, all over 2. The numerator, you want to combine that, so that'd be 2 over 2 minus root 3 over 2. So 2 minus root 3 over 2, all over 2. You're dividing by 2, so you're really multiplying by 1/2. So that's 2 minus root 3 over 4, and the square root of 4 is 2. So your final answer is the square root of 2 minus the square root of 3, all over 2. So great job if you got that. If not, take a look at the steps and see where you went wrong. Okay, and that's the last example problem for this video. So if you have any additional questions, make sure you stop in the virtual office or send me an email and we can do some more examples. Good luck.